Given an integer array nums, we need to find the subarray with the largest sum and return that sum. For example, let's say this is the given array. The answer would then be 6, since we could take this subarray and the sum is 5 minus 2 plus 3, which is 6. Notice that the subarray needs to be a contiguous slice of the original array. In other words, we're not allowed to omit the negative 2 in the middle and get a sum of 8. If we want to use both the 5 and the 3 in this array, we also must include the negative 2 in the middle. Now, the brute force way to solve this is to just calculate the sum of every possible subarray. So we would start by looking at each subarray of size 1, then calculate the sum of every subarray of size 2, and then do the same for size 3, then 4, and finally the entire array itself. After we're done, we can see that the maximum subarray consists of the middle 3 elements for a sum of 6. Now this works, but the problem is that we have to look at every combination of starting and ending indices. In addition, to calculate the sum of any given subarray, we have to iterate through the entire subarray again, so this ends up running in O of n cubed time. Now one inefficiency here is that we're calculating the same sums over and over again. For example, we calculate this sum here multiple times. So if we save our previous calculations and reuse them, we can reduce this to O of n squared time. This is an improvement, but it's actually possible to solve this in O of n time. So here's how we're going to do it. First, note that if an array consists of only positive numbers, then there really is no problem to solve. You would just include every single element to maximize the sum. This only becomes a challenge when there's a negative number somewhere in the middle, because now you have to think, is it worth it to leave out that negative number even though it means you'll have to also leave out a positive number on the other side? Or is it better to include that negative number so you can also get that positive number? In this case, notice that the sum of 4 and negative 6 is negative 2, which means that if we add both of them to our subarray, our sum would decrease by 2. So in this example, it's better to leave out those two elements because it's a net negative. This is the key idea behind the O of n algorithm. We're going to traverse the array just once, and at each step, we'll ask ourselves, is it better to include the previous maximum sum in our subarray, or is it better to exclude it? Here's an example. Let's say this is the array given. To avoid recalculating the same sums, we'll also create an array that'll keep track of the maximum sum from index 0 all the way to the current index. And this sum always includes the element at the current index. We'll start by looking at the first element by itself. This is our starting point, so the sum of the maximum subarray ending here is just itself, 1. Then let's look at the second element, which is 3. Now we'll have to ask, is it better to include the previous maximum sum or exclude it? Since 1 is a positive number, we're better off adding it to our total, so the maximum sum of the subarray ending here is 1 plus 3, which is 4. Then let's look at the next element, which is negative 6. Again, we'll ask, is it better to include or exclude the previous maximum sum of 4? If we include it, then our sum will be negative 2, but if we exclude it, it'll be negative 6. So we're still better off including it, and the maximum sum ending here is negative 2. Notice that we're using the bottom array to save our previously calculated sums, so we don't need to calculate them over and over again. Next up is 8, but now notice that the previous maximum sum is negative 2. That means we're better off excluding the previous maximum sum since it's negative, so the maximum sum ending here is just 8. Next is negative 5. The previous maximum is 8, which is positive, so we'll include that for a current sum of 3. Next is 6, and since 3 is positive, we'll include it as well for a current sum of 9. And lastly, we'll include 9 to our sum ending here for a total of 7. Now that we've traversed the entire array, all we need to do is return the maximum sum found in the bottom array, which is 9, which corresponds to this subarray here. Now before we go into the code, there's one more optimization we can make. This algorithm currently runs in O of n space, since we needed to create the bottom array to hold all the maximum sums ending at each index. But notice that for each sum we calculated, we only needed the previous maximum sum before it, and nothing else. So we actually don't need that entire array. So now let's look at the code and solve this in O of n time while using constant space. Let's say that this is the nums array. First we'll initialize a variable called curmax for current max, and initialize it to 0. This represents the values that were calculated in the bottom array earlier. and will hold the maximum sum of the subarray ending at the current index as we traverse nums. We'll also create a variable called overall max and initialize it to negative infinity, and you'll see why we do this in a second. Overall max is going to keep track of the overall maximum sum as we traverse nums. Then we'll enter the loop and traverse nums using a variable called num. The first thing we'll do is figure out the current maximum of the subarray ending at num. And remember, we'll need to decide whether to include or exclude the previous current maximum. So here, we calculate both the previous current max plus num and just num itself, and take the maximum of those two. In other words, if the previous current maximum was positive, then we'll add it to num, otherwise we'll leave it out. Right now, current max is 0, so both of these are just 2, so current max gets initialized to 2. Then we'll update overall max so that it always contains the largest current max encountered so far. So right now, the current value of overall max is negative infinity, and current max is 2, so let's update overall max to be 2. And this is the reason why we initialized overall max to negative infinity. It's so that on the first iteration, it's guaranteed to take on the value of current max, even if current max is negative. Then we'll go to the next number, which is negative 3. Since current max is positive 2, current max plus num, which is negative 1, is going to be larger than num itself, which is negative 3. So let's update current max to be negative 1. The overall max is 2, which is greater than negative 1, so overall max stays at 2. Next is 5. Now that current max is negative 1, current max plus num equals 4, but num equals 5. So we're better off not adding the previous current max, so let's set current max to 5. The current max of 5 beats the overall max of 2, so let's update overall max to be 5. Next is negative 1. 5 plus negative 1 is 4, which is greater than negative 1 by itself, so current max becomes 4. This does not beat our overall max, so that stays at 5. The next number is 8. Adding current max to 8 results in 12, which is greater than 8, so current max becomes 12. This now beats our overall max, so let's update that to 12 as well. And finally, num is negative 7, and 12 minus 7 is 5, which is greater than negative 7 by itself, so current max becomes 5. However, this does not beat the overall max, so that stays the same. We're now done with the loop, so all we have to do is return the overall max of 12, which corresponds to this subarray here, and we're done.